So in this video, what we're going to do is we're going to determine the electric and magnetic fields for the Leinard-Wiechert potentials. So I've written them down right here. Um, and so this is actually going to be kind of a long derivation. So it's probably going to take more than the 15 minutes in this video. So I'm going to group together this video and the next video for the entire derivation. So, okay, so if we want to calculate the electric field, we use this equation right here. So now we've got to find the gradient of V and the time derivative of A. So let's start with the gradient of V. Now this is going to be a little bit tricky because the distance script r is r minus this, now we're calling it w instead of r prime. So it's the change in those two distances. The velocity is the derivative of w with respect to time, and the absolute value of script r, basically its magnitude, is c times delta t. Okay. Where again, t is the time now, and t sub r is the time in the past, where the charge was at its position before it moved. Okay, so let's start. So now if we look at the gradient of v, then what we get is all these constants out front, like so. And then the chain rule applies, so you have 1 over RC minus R dot V squared, and then the gradient of RC minus R dot V. Okay, so you have those two terms. But now, if we want to apply the gradient to the thing that's in the parentheses, we have to figure out what is the gradient of RC. C is a constant, so we get the gradient of R. And the gradient of R is minus C, the gradient of the time. So in the end, we have minus C squared, the gradient of the retarded time. If we now look at the gradient of the dot product, then what we'll have is R dot del times V plus V dot del times R plus R cross del cross V plus V crossed the curl of R. So basically there are four terms when we take the gradient of that dot product. Okay, so let's look at this last equation and start doing it term by term. So the first term is R dot del times V, which is Rx ddx plus Ry ddy plus Rz ddz, all of that acting on the velocity. Okay, which means we have Rx, not partial, but R, so the x component of R times the derivative of V with respect to the retarded time, and then dt r dx. Okay, so now we have to do that for the other two terms. So for y, we get this. And for z, we get this term. like that. Okay. Which, if I look at this, I have a dv dt r. So the derivative of the velocity with respect to the retarded time, which in the end is just the acceleration. So I can factor that out of the equation, and then what I get is the r components times the derivative of the time. So in the end, what I get is the acceleration, so that's dv dtr, times the dot product of r with the gradient of tr. Okay, so that's pretty good. So that's our first term, which we've now consolidated into something a little more useful. And just to remind you, the acceleration I said was this. Okay, so now let's take a look at the second term, which is v dot del operating on r, which now we can break it up into pieces, and we'll have v dot Roman r minus v dot del w, which is that distance from the origin to the charge. And now, so we have to work out these two terms, but we can work them out the same way that we did before, which is v dot del operating on r is vx dx plus vy dy plus vz dz operating on r. And r is x in the x direction plus y in the y direction plus z in the z direction. So when you work that out, what you basically get is d dx is going to be operating on x, but give us 1, but d dx, so dy dx is 0. And so forth and so on. So in the end, what you get for this term is v x in the x direction plus vy in the y direction plus vz in the z direction, which is essentially just v. So that gives it just the velocity. Okay. So now if I take a look at that next term, v dot del operating on w, okay, so in this case, I can use my previous result, which was now the time derivative of that second vector w, and it's the first vector, in this case is v, dot the gradient of the time. So this is just like we did when we worked out the very first term in this expansion. So dw dt is the velocity, and so what I end up with is the velocity times the gradient of t. Okay, and so that's what I get. So in the end, what we have is, for the second term, v minus v dot the gradient of tr. Okay, so that's what this reduces to. So that's our second term. Okay, this is the second term in the gradient of the potential. So, okay, so let's take a look at the third term. So for the third term, we have the curl of v in there. Yeah. So the third term, well, is actually r cross the curl of v. So let's take a look at the curl of v first. The curl of v is d vz dy minus dvy dz in the x direction, plus dvx with respect to z minus dvz dx in the y direction, plus dvy dx minus dvx dy in the z direction, like so. Now we can write out these partial derivatives in terms of their dependence on t. So what we get is dvz dt dt dy minus dvy dt times dt dz in the x direction, plus dvx dt dt dz minus dvz dt times dt dx in the y direction. And we have one more term to go, and that is dvy dtr dx minus dvz dx, sorry, dtr dy in the z direction. Okay, so in the end, what is that? Well, all the dv dt's are components of the acceleration. So what we really have is the acceleration crossed into the gradient of the time. So this is now equal to minus a crossed into the gradient of the time. Okay. Okay. So we have one more term to go, but I think I'm going to stop here, and instead going to well, I'm sorry, no, I can do one last term. So if I look at the fourth term, the fourth term has in it the curl of r, which is the curl of r minus the curl of w. Now the curl of r is 0. That's not changing. I'm keeping that to be a constant fixed distance with which I measure. Like the curl of v, which we said is minus a crossed into the gradient of t, the curl of w is just going to be very similar, minus now the velocity, the time derivative of that vector, crossed into the gradient of time. Okay, so that essentially gives us all we need for the fourth term. So we've now worked out all four terms of the gradient of r dotted into v. Okay, so I'm going to stop here and then continue this discussion in the next video.